Welcome to Orbital Dynamics, Part 58. This part is based on excerpts from the book, The Mechanical Universe. Not many years ago, the only use of celestial mechanics was to compute positions of bodies in the heavens. Today, that has changed radically. As I covered in Part 1, there are thousands of artificial objects orbiting the Earth and several more traveling through the solar system. They were launched from this tiny planet we inhabit. In 1973, Mariner 10 traveled to cloud-covered Venus and then to Mercury. In 1975, the Viking landers arrived on the red planet Mars. In 1977, Voyager 2 was launched for a rendezvous with Jupiter, Saturn, Uranus, and Neptune. How do interplanetary probes reach distant planets? How do they navigate across the vast solar system? There are no free rides in space. Every trip requires an expenditure of energy. How do we navigate to other planets? The first method uses brute force. We build giant rockets, then hurl a spacecraft directly toward a planet. We then use a blast of the rockets to slow the craft down when it arrives. Here's what that looks like animated. The approach on the previous slide doesn't work. The planets are in motion. If they're in line with each other at launch, the probe will go to where the outer planet was, missing the target. From there, it drifts into the sun. The red planet is Mars, the blue is Earth. These distances are to scale. The sizes of the sun and the planets are exaggerated. If they too were to scale, they'd be so small they'd disappear. If you really wanted to do it this way, you'd have to wait until the planets are lined up in this orientation. Mars is 36 away from the Earth here. Let's say we launch our probe when Earth is at perihelion. Earth's orbital velocity at perihelion is 30,290 meters per second. We need a thrust that is orthogonal to Earth's orbit. In order to counteract both the sun's gravity and the Earth's as well, in order to counteract the sun's gravity, the Earth's gravity, and the Earth's orbital motion, the delta velocity needs to be a net 72,450 meters per second in the direction of where Mars will be by the time the probe gets there. The delta velocity vector is here. Its magnitude is 78,331 meters per second. I figured that out with the Pythagorean theorem. That's a lot of change in velocity, and we didn't account for the Earth's rotation, which adds another 465 meters per second at the equator. We're not finished yet. Let's say we reach Mars at its perihelion. Mars' orbital velocity at perihelion is 26,496 meters per second. When the probe reaches Mars, it stops. The speed from the Earth diminishes because of the sun's gravitational attraction. In order to stay with Mars, the probe will need an additional delta velocity of 26,496 meters per second to match Mars' orbital velocity. It will get some help from the gravitational attraction of Mars, so it won't need all of this delta velocity, but it will need a good amount of it. The total delta V to escape Earth and to catch up with Mars is 98,946 meters per second. While this is a fast way to get to Mars, it's really inefficient. Here's a more clever way. Here Mars is 45 degrees ahead of Earth. We launch the probe in the direction of the Earth's orbit. Rather than trying to overcome its orbital motion, as in the previous animation, we're making use of it. Here's the velocity of the Earth at perihelion. In order to reach the solar orbit, the probe has to be going at 33,689 meters per second. That's a delta velocity of 3,399 meters per second. That's the 33,689 meters per second the probe needs to go, minus the 30,290 meters per second the Earth is going. A delta V of 3,399 meters per second is far less than the 77,381 meters per second that we needed in the previous animation. Transfer orbits require precise timing. We can't send a probe to any planet at any time. The launch must take place with the Earth and Mars in the specific relative position where Mars is 45 degrees ahead of Earth. Mars' orbit is 687 days, or 1.88 Earth years. That's about 22 and a half months. The Earth and Mars will line up in this relative configuration, 45 degrees apart, every 780 days. In fact, Mars and Earth line up in any relative configuration every 780 days. We call this a launch opportunity. Opportunities like this present themselves every 2.13 years. If you miss that window, you have to wait another 2.13 years. Notice the elliptical orbit of the probe. The Earth is at one end of the major axis of the transfer orbit, at launch, and the target planet Mars is at the other end. The Sun is the central body and is at one focus. Perihelion of the transfer orbit is at Earth launching point. Aphelion of the transfer orbit is at the Mars landing point. Let's compute the precise delta velocities. If these are the two orbits, then this is the transfer orbit. The distance from the Sun to Earth is r1. The distance from the Sun to Mars is r2. The major axis of the transfer orbit is thus r1 plus r2. You'll recall that the energy of the orbit is minus g times m, the mass of the probe, times the mass of the Sun over 2a. Once we know 2a, we know the energy of the orbit. Let's call the velocity at Earth v1. The kinetic energy at Earth is 1/2 mv1 squared. The potential energy is minus gm times the mass of the Sun over r1. The total energy is kinetic energy plus potential energy. We can now equate the two energy equations. We have m on both sides of the equation. If we factor that out, we get this. We want to solve for v, so let's put gm Sun over r1 on the left. Here we're factoring out terms g and the mass of the Sun and multiplying both sides by 2. This equation is called the vis-viva equation. It was something Newton invented. Here's a more general form. You can also express it with the gravitational parameter mu in the place of g times the mass of the central body, which here is the Sun. If we take the square root of both sides of our specific form of the vis-viva equation, we get the v1 equals the square root of 2g m Sun times 1 over r1 minus 1 over 2a. Let's do the calculations for v1 for the Earth and Mars transfer orbit. G is 6.67384 times 10 to the minus 11th. The mass of the Sun is 1.989 times 10 to the 30th. 2 times g times the mass of the Sun is 2.65485 times 10 to the 20th. 2a equals r1 plus r2. That's the distance from the Sun to the Earth plus the distance from the Sun to Mars. Let's assume that at the launch point, Earth is at perihelion. That's 1.47095 times 10 to the 11th meters from the Sun. Let's assume at the rendezvous point, Mars is at aphelion. That's 2.492 times 10 to the 11th meters from the Sun. The length of the major axis of the transfer orbit is 1.47095 times 10 to the 11th plus 2.492 times 10 to the 11th. That equals 3.96295 times 10 to the 11th. Here we substitute 1.47095 times 10 to the 11th for r1, that's the distance to the Earth, and 3.96295 times 10 to the 11th for 2a, the transfer orbit major axis. The sum of the two fractions is 4.27495 times 10 to the minus 12. The product of these two terms is 1.13494 times 10 to the 9th, and the square root is 33,689 meters per second, the velocity of the transfer orbit at perihelion. Next, we'd like to know the velocity at the aphelion point, v2. Remember that for the orbiting probe, there's a conservation of angular momentum. L, the angular momentum, is r cross mv, or L is r cross p. That implies that the scalar p1 times r1 equals p2 times r2. The momentum times the distance from the pivot point is equal for all points on the ellipse. At perihelion, where the momentum is p1, the distance from the Sun is r1. Likewise, at aphelion, the momentum is p2 and the distance is r2. Momentum is mass times velocity, so mv1r1 equals mv2r2. This simplifies to v1r1 equals v2r2. If we solve for v, we get v2 equals v1r1 over r2. v1 is 33,689. r1 is 1.47095 times 10 to the 11th. r2 is 2.49200 times 10 to the 11th. That equates to 19,855 meters per second. We could have derived that with this equation by plugging in r2 instead of r1. It gives the same result. Now let's compare the velocities of the transfer orbit with the velocities of the planet, Earth and Mars. We use this equation for that. We said that the Earth is at perihelion, 1.47095 times 10 to the 11th meters from the Sun. The semi-major axis of the Earth is 1.49598,261 times 10 to the 11th meters. If we plug in the distance to the Earth and Earth's semi-major axis into the vis-viva formula for velocity, we get 30,291 meters per second at perihelion. The semi-major axis of Mars is 2.27939 times 10 to the 11th. If we plug in the semi-major axis of Mars and the distance at aphelion into the vis viva equation, the orbital speed is 21,977 meters per second. The change in velocity, or delta velocity, v, required at Earth is 3,398 meters per second. The delta v at Mars is 2,092 meters per second. That's a total delta v of 5,489 meters per second. That's about 18 times less than the 98,946 meters per second the brute force method would have taken. The brute force method is faster. You'd expect it to be. You need a much bigger rocket, however, with loads of fuel. It's a very inefficient way to get to Mars. Here's the animated transfer orbit again. In setting this up, I only considered the Sun's mass as a central body. The velocities I derived on the previous slide assumed the mass of the Earth and Mars were negligible. In reality, when the probe is launched, Earth's gravity dominates. Likewise, when the probe makes a rendezvous with Mars and gets close to it, its gravity dominates. We have to account for Earth and Mars gravity for this to be realistic. The animation looks the same, however, I've set Earth's mass to 5.972 times 10 to the 24th kilograms, and Mars' mass to its 6.4185 times 10 to the 23rd kilograms. Newton showed that mathematically celestial objects that were spherical and that had uniform density could be considered point masses. In this animation, the Earth and probe are point masses. The launching point for the probe is at the center of the Earth. Notice what happens. With the center of mass of the probe at the center of the Earth, the resulting force between the Earth and the probe is huge. That's because r is a very small number. The gravitational force is g times the mass of the Earth over r squared. If r were 1 meter rather than approaching 0, the resulting velocity would be 19,964,010 meters per second. That's 10% of the speed of light. As r approaches 0, which equates to the probe being at the center mass of the Earth, the force goes to infinity. This can't happen practically. In reality, we can never launch a probe at the center of the Earth, let alone 1 meter away. The Earth's mass is in the way. So to fix this, we'll set up a launching point at the surface of the Earth. Here we launch the probe at the target velocity of 33,689 meters per second from the surface of the Earth, which is 6,371,000 meters from the center of the Earth. Here you see the effects of Earth's gravity. It slows down the probe on its way out to Mars and sends it in a highly elliptical orbit around the Sun. The probe was launched in the same direction as Earth's velocity, but because the Earth slowed it down, the probe's orbit didn't have enough energy to get to Mars. The probe orbit ends up being a highly elliptical orbit around the Sun. The velocity of the probe's orbit near Earth needs to be 33,689 meters per second. That's what the vis viva equation tells us. In order to achieve that velocity, we have to overcome the effects of Earth's gravity first. Here the probe is launched from the top of the Earth at the surface. We send it through the Earth's gravitational field first, and then from there it goes into an orbit around the Sun. In this trajectory, it will rendezvous with Mars. This requires an initial speed of 85,868 meters per second in order to get to the 33,689 meters per second. The velocity of the Earth is 30,291 meters per second. The difference is 55,577 meters per second. That's more than the 11,200 meters per second Earth escape velocity, so we know the probe will overcome Earth's gravity. The solar escape velocity is 617,500 meters per second. 33,689 meters per second is not enough to escape the gravitational pull of the Sun. So we know this results in a solar elliptical orbit. 85,868 meters per second at the surface of the Earth isn't practical, however. The probe and its launch rocket would burn up in the lower atmosphere. We still need a better way. Let's assume we launch the probe from a high Earth orbit. I'll show you in the next section how we get a probe or satellite into a higher Earth orbit. Here the probe starts at a transfer orbit. The probe starts the transfer orbit well away from the surface of the Earth. Earth's gravitational influence is greatly diminished. In this animation, the probe starts at 15 million kilometers away from the Earth. 15 million kilometers is about 40 times the semi-major axis of the Moon's orbit around the Sun. The delta V required here is much less than 85,868 meters per second. If you want to send a probe to Venus, you have to do it differently. To reach Mars, the probe had to go faster than Earth velocity. To reach Venus, it has to go slower. Here the Earth orbit is the outer orbit, Venus is the inner orbit. The elliptical orbit, aphelion, is now at Earth. Perihelion is at Venus. Earth perihelion is 1.47095 times 10 to the 11th meters. Let's make the rendezvous at Venus aphelion. That's 1.08939 times 10 to the 11th meters. We'll use the vis-viva equation to determine the initial velocity. The major axis 2a is r1 plus r2. That's 1.08939 times 10 to the 11th plus 1.47095 times 10 to the 11th. That equals 2.56034 times 10 to the 11th. Let's make those substitutions here. If you do the calculations, you get 27,711 meters per second that the probe must travel at Earth perihelion in order to reach Venus. Earth travels at 30,291 meters per second at perihelion. The delta velocity to reach Venus is now minus 2,508 meters per second. To get to Mars, the probe had to travel faster than Earth. To get to Venus, it has to travel slower. That makes sense since the semi-major axis of the elliptical transfer orbit is less than the semi-major axis of the Earth orbit. The transfer orbit to Venus has less energy than Earth orbit. We showed that we can derive V2 by multiplying V1 times R1 and dividing by R2. Here we plug in the numbers. That results in 37,418 meters per second. Venus at aphelion travels at 34,788 meters per second. That results in a delta velocity of 2,629 meters per second. Remember that these are hypothetical delta velocities. If you really wanted to send a probe to Venus, you'd have to launch it fast enough to escape Earth's gravitational field. And when you got close to Venus, you could use this gravitational field to get into an orbit around it. Here's how you'd get to Jupiter. This requires a delta velocity of 39,000 meters per second. That's a very energetic orbit. Watch what happens when the probe gets near Jupiter. In this animation, I don't land the probe on Jupiter. I did what we call a flyby. The probe got close enough to be affected by Jupiter's gravitational field, but kept going. With respect to Jupiter, this is a hyperbolic orbit. The probe wasn't captured by the gravity of Jupiter. With a real probe, we would have done several course corrections and would have slowed down the probe so that it could rendezvous with Jupiter. Keep watching the probe. The resulting orbit appears to have a larger semi-major axis. This means it has more energy than before its flyby with Jupiter. How can this be? We didn't apply any delta velocity. It makes sense that the path would change, but why did the semi-major axis get larger? The probe got energy from Jupiter's orbital motion around the Sun. When it's under the influence of Jupiter, there's kind of a slingshot effect, where energy gets added to the probe's orbit. Energy in the universe must be conserved. The probe would have slowed down Jupiter somewhat, but not appreciably so given their relative masses. On the other hand, Jupiter sped up the probe significantly. This is a very common technique for sending probe great distances from the Earth. If you take advantage of a planet's orbital motion around the Sun, it will kick a probe into a more energetic orbit, saving precious fuel. Giuseppe Colombo, nicknamed Bepi Colombo, was an Italian scientist. He developed a method for getting a spacecraft into an orbit with Mercury. It involved multiple flybys and several delta Vs that required fuel. Mariner 10 used this technique, and the new Bepi Colombo mission to Mercury will use it as well. This method takes 6.5 years to get a probe from Earth to Mercury. Many think that if Apollo 13 had not landed on the Earth, the capsule would have orbited around the Earth in a highly elliptical orbit for years. Engineers at Analytical Graphics Incorporated, the company that makes Satellite Toolkit, ran a simulation with the Earth, Moon, and the Sun in their relative positions on the day in 1970 when Apollo 13 tried to come home. Here you see the capsule missing the Earth. This was a possibility that everyone feared. The capsule does indeed go into a highly elliptical orbit around the Earth. By this time, the astronauts would have perished. It would have been horrible had they orbited the Earth for centuries. But notice what happens in the second orbit. As the Moon gets closer to the capsule, it alters the capsule's orbit. The resulting orbit puts the capsule on a collision course with Earth. Had the astronauts missed Earth on the first pass, they would have crashed home eventually.